So, hello everyone. My name is Gando. I'm from Toshiba Corporation. Today I'm going to give a talk to report a evaluation method of gas permeability for micro-scale thin polymer film. I'm going to use the encapsulated MEMS stamped oscillator. Okay, so this is the outline of my talk. First, I'm going to introduce my background and the goal of this work, followed by a brief overview of the theoretical background and the method we're going to use for the coming experiment. And then I'm going to explain how we fabricate the sample and its specification, followed by the experiment and result. Let's start with the introduction. So obviously the market of MEMS is going really fast thanks to the coming age of IoT. And in terms of mass production, so key issues for the MEMS devices are small size, we need low cost and a low parasitic capacitance, and most importantly, the high reliability. As one solution, we have come up to a MEMS embedded with CMOS circuit under it, and this system is covered by what's called a wafer level chip scale package we call WLCSP. And we have been developed a tunable capacitor called RF MEMS for over 10 years, and we have adopted this WLCSP structure. Let's come to a closer look at this structure. We got a panel actuator inside, and this is the MEMS here, the top electrode and the fixed electrode under it. And the MEMS here is surrounded by a package here, and we call it thin film encapsulation. And this is made of a multiple layer, consists of insulating films and polymer films. So the matter we are considering is that the MEMS is actually interacting with this ambient gas in the package. So the surrounding pressure and atmosphere directly determines its mechanical performance and durability. So we have to, one thing we want to do is the pressure monitor, and we next want to control the pressure inside the package. So I say the target of my work like this. The first one is we want to monitor the internal pressure. Then I want to understand the gas permeability of this package, which is a target of this work. So the theoretical background. First, I'm going to introduce a little about the damping oscillation. And the physical system we're considering is a movable mass, a proof mass, in a viscous gas, say air, and the movable part is connected to the anchor, the bottom, with a spring. And the equation of motion is written in this way. We have to consider the spring force, the damping force, and this is displacement. The theoretical solution standard for this equation is a product of attenuation and oscillation with the initial displacement. And this is a waveform, simulation waveform of the displacement against the time. And we can say attenuation and oscillation here. And this waveform can be described by a dimensionless factor called the Q factor. And it's defined by the initial kinetic energy divided by the energy loss per circle. And here the loss considered here is mainly the loss from the air damping force. Here's and the Q factor is inversely proportional to the pressure here. At high Q factor, the oscillation is big, which means it's low pressure. Okay. The next part of theory is a gas permeation. The system we're considering is a hermetic box with a volume V, and it's initially filled with gas here. And one side of this box is sealed with a polymer film as a specimen. And here, thanks to the pressure difference between the inside and outside, gas does permeate proportional to the pressure difference. And as a result, the pressure against the time should following a decay of exposure law here. And the time decay constant here has its relation with the gas permeability K in this way. And this formula is telling that once you can measure the time decay constant, you can actually calculate the gas permeability from other geometric parameters. Here comes the sample fabrication. It's a digest one. So I started with the formation of the movable part electrode on a sacrificial layer made of polyimide, and above it I deposited another sacrificial layer 2 in order to form a insulator dome, and it's IO2 dome in this case. The point here is that I'm going to open the dome with holes from the etching process. Then I'm going to get rid of the sacrificial layers inside by the etching process. Here comes the sample called sample A here. In this way, the MEMS oscillator is interacting with the air inside and outside the air. And the next sample here is that we're going to seal this dome with specimen polymer film. As a result, this is a optical image of our product. It has an octagon structure with a diameter of 500 microns, the top view, and this cross-section view. The geometric parameters are listed in this table. Note that the polymer film thickness in this case is 1 micron. Okay, I'm going to explain my experiment. This is a system here. The operation, the basic concept of operation is that first you have to apply a voltage higher enough than the threshold to get the MEMS pull in. And if you turn off the DC input, MEMS is going to pull out like this way, and we can expect displacement. And the displacement against the time will be the damping oscillation as I have mentioned here. And this is the circuitry block diagram of circuitry system. And 2 points. First one, the displacement here is observed by the changes of capacitance from the input and output of a radio frequency signal. The second is that the device under unit is put into a chamber here, and the pressure inside chamber can be controlled from 0.1 kilopascal to around 100 kilopascal here. And the waveform is finally stored in oscilloscope. So the flow of the experiment, we have 2 experiments here. The first one is using sample A here to obtain the relation between Q factor and the pressure. And in the chamber, the pressure are changing from 2 pascal to around 100 pascal. The second experiment here is to use dome filled with specimen polymer film under a vacuum chamber. And I'm going to see the time dependence of the pressure inside the dome here in order to measure the gas permeability. The first experiment here, I'm going to show the results. See, if we have this is a waveform at 2 pascal, it's very low pressure, we can see large amplitude and many oscillation forms here. And as the pressure goes up, the numbers of oscillations decreases. And around 3 kilopascal, the oscillations actually disappears here. So it changes at different pressures. So how are we going to quantitatively determine that? Is we use a Q factor. So this is a waveform here at 0.5 kilopascal. And if you calculate the amplitude ratio between the first largest amplitude and the second largest amplitude, the Q factor can be calculated in this way. And in this case, the Q factor is 6. If you're going to do this analysis for all the waveforms I have observed, I'm going to get a data like this one, a Q factor against the pressure here. And the data point can be decomposed into 2 parts, the pressure-dependent part and the pressure-independent part. The pressure-independent part are coming from the surface loss, anchor loss, and other summer discussions. And what we're interested in, the pressure-dependent part is inversely proportional to the pressure here. And if we use and this model can be written this way, and we use the best fit parameters are in this formula. And using this formula, we can actually measure the pressure using the Q factor from around 0.1 kilopascal to 5 kilopascal. So the next experiment is going to be, we put a sealed dome into a vacuum chamber here. Then we observe the waveform changes against the time. Here at the beginning, we do not see any oscillations here, which means that the pressure is really high inside the dome. And at around 7.5 hours, with some oscillations, which corresponds to a Q factor of 3.7, and that goes up as time goes on. So this directly means that the pressure is decaying in the cavity as time goes on. So if we can convert these Q factors into the pressure from the relation I've obtained previously, we can finally obtain a approach like this one. This is the time under vacuum in linear, and this is pressure in low here. And the data points are following a drop, linear drop, which means the pressure is decaying exponential low. And if I use the best meanest square method to obtain the best fit of the slope, the time constant, it is 2.8 hours in this case. And I use this parameter in this equation here, and with other geometric parameters and temperature, I can actually calculate the permeability. That is around 1 to the minus 16 mole per meter per pascal per sec. I'm just going to demonstrate that with this method we can calculate the gas permeability. This is quick. So this is a summary of my talk. Experimentally we have obtained a model for the Q factor pressure relation for a MEMS actuator, and we measure the gas permeability for thin polymer film from the pressure time dependence. I hope that this work is going to be useful in the reliability evaluation for small and thin packages of MEMS devices. This is the end of my work. Thank you.